second, we will see if we can get Rainer to speak.
The topic of my presentation, sorry for this technical glitches here, is a measurement of methane from rice fields, best practices and advancements. And I'm at the moment consultant for the International Rice Research Institute, my former employer. Let's first have a look at the greenhouse gas budget and the closed chamber method. Most of the rice fields are flooded for at least for some time of the year. Then there is a lack of oxygen, anaerobic conditions in the soil. So the decomposition of soil organic matter leads to methane. There are different pathways how methane can get out. It can go through the diffusion, which is very low because the solubility of methane is very low. It can go through evolution, or it can go through the through the rice plant, which is the most important pathways altogether. So then that is methane, but there is also another greenhouse gas, nitrous oxide, which also produced by microbes, and it's a function of the amount of nitrogen that is applied. So now, if we want to measure it, the easiest thing is to put a chamber on top of that. The chamber has typically a kind of a frame that stays throughout the season in the soil to reduce disturbance, and then we put the chamber there on top to enclose the head space, so that we will have then an increase in the concentration of the greenhouse gases in the head space. Yeah, then we need a fan to mix the whole area, and then we can retrieve samples with a syringe going through a septum. These samples can then be stored ideally, or we bring it directly to the GC if that is possible. We can store it, and then we analyze it in a gas chromatograph. So at the end we will get a series of concentrations, ideally a linear increase in the concentration, and from the slope we can then determine the emission rate. These chambers come in various designs and sizes and shapes. Here just a few examples. So as I said, we have to avoid any disturbance. So typically they have a kind of some planks here. Sometimes they are segmented, and at IRRI we also used a lot of automated chambers that record the emissions over 24 hours over the entire season, and we also put these kind of systems in different places in Asia. You see it here even in deep water rice. There are handbooks on that, so you can really get clear instructions how to construct them and how to operate them. So in different organizations have published it. They're even available in some local languages. What are the advantages of those chambers? Well, number one is really low investment cost. That is quite obvious. Number two is that they have a high mobility. So it makes this approach especially suited for comparative measurements, which is something we really want to do typically in rice fields for comparing the baseline with the project and so far. There's a straightforward design and operations, but of course we have to follow consider some precautions, avoiding soil disturbance at sampling. The chamber exposure should not exceed 30 minutes to avoid the damage of the plants. And then we have to consider also the storage that should be in some airtight vials. But nevertheless, there are constraints. Let's start with the spatial variability. The chambers should ideally cover large areas, but that makes them very heavy, and that is really quite difficult then to place them somewhere else. So far there has to be some sort of compromise between number one, large area, and number two, mobility. If we want to have a standard errors, so basically what is the rule that we need at least 3 replicate chambers in the field, and that is also done by most of the measurements that have been published or have been used so far. The next constraint is temporal variability. Given limited laborability, most chamber measurements were done in weekly intervals with, you may say, only one measurement on a given day. And that's, of course, a problem because we know that within a day, there are changes. There are diurnal patterns. So these are some data that come from automated measurements. So there are basically thousands of individual data points over 3 seasons here. And you can see they are plotted here according to daytime, and there is, as somehow expected, at midday or the early afternoon, we have a kind of a peak. So it's really a question where should we measure that. What most people are doing is really that they make these manual measurements at around from 8 to 11, which is a period that you're avoiding the very high or the very low emission rates. The next constraint is now the detection limit, which is especially important for nitrous oxide, because nitrous oxide fluxes in the rice are typically very low. We have to understand that the detection limit in the chamber setup is of the detection limit of any greenhouse gases, not only N2O, but for methane, usually it's not a problem because the fluxes are higher. It is an inverse function of the chamber height. Thus, we can improve the detection limit by using shallow or segmented chambers. And that is done, for example, in those kind of measurements where the investigators are specifically interested in nitrous oxide emissions, so then they can really use shallow chambers to have higher detection limit. Or we could think about segmented chambers that at least in the early stage when the rice plants are small, and of course we have to include the rice plants, that what I said before already, that a lot of emission goes through the rice plant, that we can then have higher emission rates in the early stages of the when fertilizer is applied, and maybe later then it's not that good anymore. But there is also something to consider if we even have the flux rate, the result is below detection limit. That may sound at first as if the measurement has failed, but that's not quite the case, because we have evidence of very low emission rates, and that, depending on the context, could be a very important finding. For example, there is always the concern that AWD is increasing the emissions of nitrous oxide, but when we show, okay, the flux rates are below detection limit, we can at least say that has not happened under these circumstances. New development now, also part of my talk here, that what is new is really now that there are lasers available that are really very mobile and very robust. Of course, lasers as such is nothing new, but before they were extremely sensitive and also needed a lot of space and were not really mobile. But that has really changed now. These kind of lasers, if you think it in combination with the chamber measurement, can really become now a game changer. The time response is extremely low, or 2 seconds. The response time is only 2 seconds, and also the detection limit is much better than what we can ever expect from a gas chromatograph. And so far, it's really a new ball game now, that we can really try to use this kind of laser with a very different setup of chambers. Much faster measurements can be done in the field. So we're really hoping that this will improve also the database, and that IRRI, we have now started a new project in which we are using this type of lasers. There are things that can be done completely without chambers. There are also approaches completely without chambers. That is the eddy covariance technique. What we need here, the eddy covariance technique for measuring methane. I mean, eddy covariance has mainly been used for carbon dioxide. What we can do is we need an analyzer for methane, and we need an anemometer that records the 3-directional wind field. But the problem is that we need a very large area for that, because the wind direction from any wind direction from any region, we need 100 meter fetch, meaning the wind coming from any direction should have at least been 100 meter homogeneous, area of the rice field. And so we need here, as you can see, we have these experiments with 4 hectare plots, which is really quite big. So in other words, you can hardly do it for comparative measurements. The whole approach works like this, that the wind is horizontally going to the center, and then there are these eddies that are going up and down, and with our 3-dimensional wind field, we can then calculate the concentration, we can then calculate the net flux going up, or in fact, even for carbon dioxide, then even going down. However, we need a very high frequency to really capture these eddies. So it's here 10 hertz, meaning 10 times per second is typically the frequency we use for eddy covariance. So why do I show it, even though I said before it's not usable for the voluntary carbon market at the moment? Well, I wanted also to show how complex the dynamics is over the rice field, how complex these flow pattern are, and so far that is also basically an introduction to the last slide that I have before my conclusion, and that is about remote sensing with satellites. Of course, there are no satellites available that can measure the methane concentration, but the concentration itself may not really say anything about the flux itself. I'm not an expert in this field, but I found a really very good review paper that you can see here, Jacob et al. just from last year, and they consider these point source images. And as I'm not an expert, so I rather give a quote from that paper. What they're saying is that these current point source images with a detection threshold, and that's now really interesting for us, of 100 to 10,000 kilogram methane is the context here per hour range, that enable monitoring of large point sources. To put that into perspective, the IPCC default for methane from rice field in Southeast Asia corresponds to 0.05 kilogram CH4 per hour per hectare. So in other words, to go to that level, you need very, very large fields. But of course, these detection limits are not carved in stone. They may also improve. Even the authors talk about using tracers in the future. I know there are many groups that think about artificial intelligence, so maybe that's improving. Maybe there is a point where these two can meet in the future. I'm not an expert, as I said, so I don't want to speculate, but yeah, of course, technology evolves, and so we cannot at least not exclude that. So in conclusion now, chamber measurements have undoubtedly their shortcomings, but at present there is no reliable alternative available. However, in the future, this may improve with ongoing progress in the analytics. I showed the laser analytics, which may be in combination with chambers, but in an improved setup, and then, of course, also remote sensing techniques. So with this, I'd like to stop it. I hope you have heard me. I have no idea whether this has worked or not. Thank you very much. I'm just going to stop my presentation now. So, good.